All right, so today we want to treat a cover requirement for our pre-stressing force. Now, in dealing with the cover requirement, we're going to start with the equations. Dealing with cover requirement. Now, in dealing with cover requirement, we're going to have three cases, which is case one, case two. Most likely, we're going to be dealing with two cases, case one and case two first. Now, for cover requirement in non-composite sections, we are going to look at case one. For case one, a case where we have M1 and M2 to be positive, and case two where we have M1 and M2 to be negative. Now let's look at case one, starting with case one. Now case one is peculiar to simply supported beam where you have sagging moments all throughout the span of the beam. And of course, we know that the maximum cable eccentricity is K1. Let's assume that our eccentricity, let's start with equation 3A and 4A, which are the upper limits to cable eccentricity, uh, uh, which represent the limit to cable eccentricity. We're going to start with equation 3A and equation 4A. Let's start with that first. Or better still, we can start with equation 1A and 2A. So starting with equation 1A and 2A, let's start with that. We have that EX is equal to our Z1 over A and F maximum minus N1 bracket Z1 over P or close bracket M1 over P, equation 1A. Now, that is equation 1A. Now, let's start off with equation 3A. Equation 3A represents the maximum equation 3A equation 3A and 4A will be used to obtain the cover requirement for a case where we have positive and positive moment for M1 and M2. So we'll go by equation 3. We'll have equation 3 as ES lesser than we have Z1 over A minus bracket F minimum minus N2 bracket Z1 over P or bracket M2 over P is equation 3A. So solving equation 3A, the first thing we will do, we needed a solution, equation 3A, because we're solving equation 3A and equation 4A. So we're going to have a graphical solution for both of them to obtain our maximum cable eccentricity. All right, so for write equation 4A as F maximum minus N2. We'll have Z2 over P minus Z2 over A, or bracket M2 over P 4A. Okay, so solving this simultaneously, we're going to have the expression in a graphical format, but we're going to plot a graph of the two variables, which is M2 and P. M2 appear the two variables. So while we have M2 on the vertical axis, we will have P at the horizontal axis. So in doing that, let's derive the expression for both we can say from equation 3A. We're solving this, we're going to have M2 over P. All right. And I'll have ES. Okay, then we have minus F minimum N2 Z1 over P. So this becomes the expression for this. Now, having done this, we can look for our P. We can say that I look for M2 become lesser than Z1 over A plus ES bracket P minus F minimum minus N2 Z1 over P. Okay, so this becomes the equation So comparing this with equation of a straight line, of course, this becomes our slope, while this becomes our intercept uh, at the y-axis. Okay. Now, this is what we have for this particular graph. So the next one we are going to have is, let's take a closer look at it. All right, so multiply this, we have this. Okay, so this one is going, so this one is no longer there. So we have this as our equation. Now let's look at the second one, which is equation 4. I'll say from equation 4, we have, uh, from equation 4, we have it as m2 over p is lesser than f maximum minus n2 z2 over p minus z2 over a. All right, z2 over a, then we have minus es. So we have minus es. So that's what we have for equation 2. All right, so if we do that, we're going to have that m2 is lesser than, multiply all through by p, we'll have f maximum minus n2 z2, okay, by p. Then we have this other side of it, which is, we bring out p, we can say z2 over a plus es. All right, so we can have that, so that we can now rewrite this, where this represent p bracket z2 over a plus es plus f maximum minus n2 z2. So this becomes our next expression. So now we have two basic expressions we've been able to derive. This is first expression. Let's call this one from equation. We can call it whatever. Can we just call it, let's say, equation 11? We've already got an equation. Let's call it equation 10. And let's call this one equation 11. So I have equation 11 and we have equation 10. So we're going to solve for both. Now, solving for equation, how are we going to do that? We're going to plot a graph for both of them. So let's quickly plot the graph and let's obtain the solution for cover requirement for this case. All right, so having looked at the solution to the graph, we can see that the solution, let's call it x. If we call it x, we'll say maximum cable eccentricity for cover requirements. So our eccentricity, let's assume it to be negative Ka1. Our Ka1 is our cable eccentricity with respect to fiber number 1, which is a zone where we have maximum moment, maximum positive moment. So remember that we've taken a sign convention that our eccentricity below our neutral axis should be assigned negative. So we have Ke1, which is maximum cable eccentricity for cover requirements. We are calling it negative Ke1. So we're going to substitute it into equation 10, which we've gotten before. So doing that into equation 10, equation 10 is further simplified, and then we're going to have it as it is. M2 less than Z1 over A plus KE1, all enclosed bracket P minus fiber stress minimum minus N2, or into bracket Z1. All right, so that gives us the equation. Similarly, we are going to substitute that same value of negative eccentricity, negative maximum cable eccentricity, Ke1, into our second equation, which is equation 11. And if we do that, we are going to have equation 11 in a similar fashion as it is on the board. So having gotten that, the next thing we are going to obtain is the solution to the inequality. Of course, the inequality uh, is going to be obtained. The solution is going to be obtained. Let's call that solution, which is the point of intersection of the graph. Let's call it x. So if we have that to be x, so we can look for the pre-stressing force x. So obtaining the pre-stressing force, we do that by equating both equation 11 and equation 10. All right, so equating equation 11. So equating equation 11 and equation 10, we are going to have our value for x to be x is equal to z 2 bracket f maximum minus n2 plus z1 bracket f minimum minus n2 all over z1 plus z2 by a. So that gives us the critical value for our pre-stressing force. Now, we must not exceed x. In choosing your pre-stressing force, do not go beyond x because it's not going to be economical. So it is advisable, if you are carrying out your design, if due to high moment there is need for you to increase, or there's need for you to have a pre-stressing force that is greater than x, it is recommended that you peg your value at x, or better still lesser than x, better still within or lesser than x rather, and you can choose around that zone. Any value above x for pre-stress is going to be uneconomical. So, and also ensure that in a case where it becomes necessary for your pre-stress to be increased, instead of increasing the pre-stress to get your cover requirement, you just need to do increase your section so that you can have adequate cover for your section. Okay, so that is that for this first case. Now remember, this case is a case for M1 and M2 both positive. So let's look at the value for our pre-stress, the value for cover in case 2, which is negative. Also take note, for practical sections, our KE1 for practical sections, our KE1 must be greater than sectional modulus with respect to fiber 2 over area. So for all practical sections you are going to be dealing with, you should expect your KE1 to be greater than Z2 over A. Also from equation 10, we can rewrite equation 10, and we can obtain the pre-stressing force within boundaries that are lesser than our x. So for us to obtain our pre-stressing force, those are areas covered by equation 10. So in solving for equation 10, let's look for our pre-stressing force for values lesser than s. Let's call it P10 for equation 10. So we'll call it P10. So if we do that, we can have our pre-stressing force, our pre-stressing force within that zone to be P10, and the value for P10, the expression for P10 is C. Our P10 is M2 plus fiber stress minimum, fiber stress minus N2, and Z2. We have Z1 over A plus KE1. All right. So this is the first requirement for cover. Now we'll look at case 2. Case 2, we say let the maximum cable eccentricity ES becomes a KE2, which is cable eccentricity with respect to fiber 2. Remember, we are the support of the beam, and we are going to be having our K, our maximum eccentricity, to be positive because at this point it is above the neutral axis. Okay, so the cable zone equation will be considered, which is equation 1A and equation 2A. So in a similar fashion like we did for equation 3A and 4A, we are going to do the same, and we are going to obtain the stationary point of this inequality. I call it y or x. Then we look for the limits. All right. Now, all right, take note that our equation 5 is greater than equation 6, like we said in a previous video. So we have equation 5 greater than equation 6. Although, whichever way you do, whether equation 6 greater than 5, you're still going to boil down to the same thing. So let's not bother ourselves with that. So let's go to case 2, like we are saying, and let's consider equation 1a and equation 2a. Now from equation 1a, we have z1 over a, all bracket z1 over p. So this is what we have from equation a, equation 1a. So we can solve this by saying m1 is greater than multiplied through by p. We are going to have z1 over half. So if we want to do this, we are going to say, how are we going to get this? So remember, our k E2 is going to be substituted for ES. So we're going to be having this as M1 greater than Z1 over A minus K E2. All right. P minus F maximum N1 Z1. All right. So this is the first we're going to have from equation. Let's call this one equation 12. Now let's go to the next one, which is from 2. We go from equation 2. We have equation 2, the same thing as M1 greater